Kindly type them. I'm using the chat function, and during the question and answer session, I will raise them up. I'll raise your questions up to the speaker for him to answer. So with the house rule said, I'll introduce the chapter coordinator, who would give a short address and introduce the program chair. Thank you for your time. Dr. Abimbola Drobito is the chapter coordinator. Over to you, sir.
Thank you very much, Mr. Koyemi. Thank you for that great introduction. Good morning, Canada, US. Good afternoon, Europe, Nigeria. Under the leadership of our president, Mrs. Patricia Oshobu, fellow of NAPE, I welcome you all to NAPE UK Europe chapter second technical meeting as stated. And I hope that everyone is keeping safe. And as you know, the topic of today's event is the next level of non-destructive testing with IWEX 3D ultrasonic imaging. This is going to be presented by Dr. Niels of Apples. And without wasting too much of your time, I would like to introduce the chairman of today's event. He is a fellow of NAPE, lover of our chapter, NAPE UK Europe chapter, and also past president of our Grace Association, who is going to introduce the speaker, and the person is Mr. Ajibola Oyebamiji, FNAPE. Over to you, sir, Mr. Ajibola.
Okay, I believe you can hear me.
Yes, we can hear you, sir.
Okay, thank you, Dr. Abimbola Drobito, the chapter coordinator of UK Europe. Thank you for the interest in always wanting me to be the chairman of your technical activities. Thanks to your very hardworking executive committee members who are working with you for quite some time now. I'd like to thank also the speaker for today, Dr. Niels, who will be speaking to us on the next level of non-destructive testing with this new, probably new technology. So I will go straight forward, straight ahead to introduce the speaker without wasting too much of our time. Dr. Niels is a technical authority at the pipeline department, a specialist in ultrasonic non-destructive, that is NDT technology, level 3. He has a PhD in ultrasonic imaging with IWEX at Delft University of Technology in the Netherlands, and an MBA at Rotterdam Business School. Dr. Niels has over 20 years of experience in ultrasonic inspection and technologies, from research and development to the application and implementation. Distinguished guests, ladies and gentlemen, I'd like to invite Dr. Niels to go ahead with his presentation. Thank you.
Okay, thank you, Mr. Chairman. Thank you for your kind introduction. I'm sharing my screen, so I would just like to confirm if my screen is visible to the audience.
Yes, it is, Niels.
Okay, excellent. The content of my presentation indeed is to talk about the next level of non-destructive testing with IWEX 3D ultrasonic imaging. The kind words of the chairman has already introduced myself, so I will skip this part. And I would like to share with you the content of this presentation. So what I have prepared for you is a bit of a background story, the basic concepts where I would like to introduce and where I would like to discuss the reason for non-destructive testing and more related to the pipeline application, namely the inspection of the girth welds. So we know that for quality purposes, pipelines, girth welds, they need to be inspected. So we have a quality assessment, and that quality assessment can be done by means of ultrasonic inspection. And to set the scene for the main part of the presentation, I would like to revisit some of the traditional ultrasonic inspection methods, namely the manual inspection methods and the automated ultrasonic inspection methods. From those basic concepts, we will see that there is room for improvement. Yeah. So although we have existing technologies based on ultrasonic inspection for the quality assessment, we will see that it's not always straightforward to do the interpretation and that there is some serious limitation of these inspection concepts. And therefore, we spend a lot of time on research and development to see if there are possibilities to overcome these limitations. If we, for example, look at other application fields, then we see that non-destructive testing in general has seen many facts of progress. So, for example, computers are more powerful, they are faster, storage capacity, and basically advances in that kind of technology enabled the development of ultrasonic imaging. So what I would like to do is share with you some of the principles of ultrasonic imaging. And basically, my intention is to give you an appreciation about the benefits and also to get a conceptual understanding of the differences between existing technologies and the new technology, which is IWEX. Then, so much for theory. I would like to share with you some examples from practice. So the examples that I've prepared for you are from actual operational situations. As we speak, there are multiple different applications, but I would like to narrow it down for you a bit and talk about the applications in carbon steel. So I would like to show you some examples of small welds with small wall thicknesses, medium and heavy wall thicknesses. And also, I would like to share with you some video clips where you can actually see the inspection strategies in action. Then I would like to conclude with some words about industry acceptance, because it is very important that any new technology which has been introduced, that becomes accepted in our industry. And as we speak, the IWEX methodology is becoming accepted by codes and standards, but also through qualifications that we have performed. Then I would like to summarize a bit of this presentation, and I'm sure there is some time for questions. And yeah, I hope we have a good discussion. But first, let's talk about the quality assessments of welds. Obviously, the main purpose, which is very important, is that we check the integrity of the welds. And why should we do that? Well, because if welding practices are not optimal, if welding practices are poor, that can lead to different kinds of indication, different kind of defects in welds, and those welds form then a weak spot. So what can happen is if the pipeline is under pressure, or if the pipeline, for example, is under a fatigue scenario, could be due to wave motion, could be due to landslides, and any sources that can put stresses on the pipe, then the girth weld is typically the weakest spot and will lead to failures. So what kind of indications are we talking about? Well, there's just a few here that you can see. There's the lack of fusion indications, the porosity, lack of cross penetration. There's well, different kinds of indications, volumetric and linear, that can actually be in the weld, and those are the kind of indications that we're looking for during the quality assessment, because those type of indications form the weaker spot. Also, as a bit of a background, the pictures that you see here are from obviously from real indications. In the United States, the Department of Transportation, they keep up with records of failures. So these situations are actually from real life, and I would like to stress the importance of the quality check of the girth welds, because, well, as said, this is just some examples, but they can lead to catastrophic events, health and safety threats, but also obviously significant environmental and economic damage. So this is what it's all about. And let's talk about some traditional ultrasonic methods. So we are very much aware that we need to check the integrity of the welds. In earlier days, and actually still, the quality of those welds can be checked by means of radiography. However, radiography has some fundamental limitations. One of the limitations of radiography is that it's hazardous. We are working with X-rays or other other hazardous sources. So then traditional ultrasonic inspection offers a benefit because it's not hazardous for the human being, and it's a very efficient way to find indications. So when it comes to traditional inspection, you can basically say there are two different categories. You have the pulse echo method and the TOF method, and basically the principles of these methods rely on the fact that ultrasonic waves can propagate through the material, they can propagate through metals, they can propagate through water, and then in case there is a defect in the weld, then we see that ultrasonic waves reflect at that indication, and that means that we can receive that reflection. So the pulse echo method basically relies on ultrasonic waves that are focused, much like a laser pointer. It's a very small directional beam, and well, the benefit obviously is that you can detect indications, but it does require that small ultrasonic beam has to be pinpointed at exactly the case where the indication would be. So the sizing based on the pulse echo method, because detecting an indication is one thing, but obviously once we have detected an indication, we also would like to understand if it's significant, because very small impurities, they may not compromise the integrity of the weld, but obviously very large indications, they do compromise the integrity. So apart from detection, we also would like to say something about the defect size. With the pulse echo method, typically that is done by means of a reference method. So that means we calibrate our system on a target that is known. And then once we detect an indication, then we correlate the image, or then we correlate the response from the indication with the response that we have obtained from our calibration reflector. Then we have the TOF method, also pulse echo, or it's also ultrasonics, but the arrangement is a bit different. It does not rely necessarily on small directional beams. It relies on a broad beam, and basically what you try to do is you try to hit the indication with a lot of ultrasonic energy, which causes the indication to vibrate, and that vibration causes the tips to diffract, and those tip diffractions can be then detected. The signal to noise ratio, because of the fact that it's diffraction, is typically very low, but the benefit is that you'll have the upper and lower tip, and then sizing is based on a triangulation of the upper and lower tip. The typical kind of displays that we expect from traditional UT, and that is what you can see here, they come in a large variety. Yeah, so you have A scans, B scans, sectorial scans, linear scans, and one of the reasons that I'm sharing this picture with you is that it's not straightforward to understand what we are looking at. So usually it's let's say relatively easy to understand that there's an indication because we receive a response. But from these pictures, I think it's understood that it's not easy to do the interpretation and to size, or characterize the indication. Then if we move on to automated ultrasonic inspection, so basically automated ultrasonic inspection can be considered as a combination of the previous mentioned methods. So typically we have the pulse echo method and the TOF method integrated in one frame, as you can see it here. The philosophy of this automated ultrasonic inspection setup is that we would divide the weld into depth zones, and then each zone will then be inspected by its own dedicated ultrasonic beam, and also in combination with TOF. So you can imagine this setup is quite complicated. It does require a setup procedure, and that setup procedure also requires these specific calibration blocks, because in order to calibrate, for example, one zone, we assume that the indication, so for example, a lack of fusion indication, has the orientation of this weld preparation. So the targets that are in this block are intended to represent lack of fusion indication of this weld. Now, this works, but it does require tight tolerances for the calibration block, and also it does require strict requirements for your setup. So to share with you some of the AUT data that comes from this automated ultrasonic setup, here you can see a typical strip chart, and again, I think it is fair to say that it does require some expertise to do the interpretation on this. Having said that, by no means I would like to disqualify this technology, because at the moment it is the most renowned technology. There are codes and standards, and the technology as we see it over here has proven itself many times, and it's common practice. So by no means this is something that I would like to disqualify. But the reason that I'm sharing this with you is that there is room for improvement. And that improvement comes from some of the limitations that I have summarized here. And from this summary, I would like to make a step towards the new technology, which I think is nicely illustrated based on these limitations. So as said, the detection of defects depends on variables, which cannot always be controlled. For example, the orientation and shape of defects, that is what it is. And if we are trying to find indications with directional beams, that means that we actually assume what that orientation would be. And that doesn't always have to be the case in practice, because real-time indications, they may be irregular, they may not have the same orientation as we expect, and that means that it has a consequence on our inspection performance. Likewise, variations in geometry, sometimes the wall thickness changes, sometimes, due to the welding, there is high-low, or there is a large cap or root reinforcement. Those type of geometrical features is something that we cannot control before we do the inspection. Likewise, the probe, if we have a guiding band in an automated sense, then that setup is something that is very hard to control. So as a consequence, the data presentation, it comes in many different displays, A, B, C, D, S scans, whatever letters we have in the alphabet. It doesn't necessarily make it easy to do the interpretation. And sometimes we see that different inspectors, they come up with different results, although they have exactly the same scans. So sizing of defects often requires test pieces, and the setup does require these calibration blocks. So having set the scene, having talked about the traditional inspection methods, the pulse echo method, TOF method, automated ultrasonic inspection based on the zonal discrimination. Now I would like to make a bridge towards the improvement that we would like to present. So first I would like to introduce some of the principles. Ultrasonic imaging, as the name suggests, we are talking about an image. An image for this type of inspection is much like an image that you would take with a digital camera. Yeah, so if we would take a picture with a digital camera, that picture itself is basically a pixel volume or area. Yeah, so if you can see here, for example, I have a girth weld and I have a cross section, and here you can see an image area, and that image area consists out of pixels. And basically, this area with these pixels, that is something that we're trying to fill. What we use is 2 ultrasonic probes, and these probes are actually arrays. Yeah, so here you can see number 1, and then we have 1 to 64. So in this setup, we use 64 elements on one side and 64 elements at the other side, and each element can generate an ultrasonic wave. And also, each element can receive ultrasonic waves. So this is basically the main setup of what we will use to construct an ultrasonic image. And again, the ultrasonic image will be a picture that consists out of pixels. Okay, so now we have defined our setup. I'm trying to share with you some of the principles again and try to explain how it works. I can understand that this might be a bit complicated, but I think, again, the intention of this presentation is to to obtain a bit of an appreciation and to share with you some of the conceptual differences. Okay, so here again, there's a setup, and basically how we can create an image, how that is done is that it requires a model. What do I mean with a model? Well, basically we have 2 wedges. We have a wedge angle, we have the position of the array, and we have defined our image area. That image area has pixels. And one thing that we know before we do the inspection is we know this model. Yeah, so that means that we know what this wedge angle is. We know what the vertical or horizontal index is. We know our element pitch. We also know the location of this pixel. So basically, this model is known before we start the experiment. Now, one thing important to mention is it does not require any knowledge about the weld configuration, right? It also does not require any pre-knowledge about orientation of indications. The only thing that it requires is the model itself. And it does require the definition of this, let's say this pixel space, this image space. Now, these elements that you can see here, they can be used as sources and receivers. So basically what I can do is, because I know this model, I can calculate the travel time from an ultrasonic wave from this source to this pixel location and back to any given receiver. That is something that I can calculate anytime I would like. Now, in case something would be present at this pixel location, for example, a defect, could be lack of fusion indication, it could be a pore, it doesn't really matter. But in the event that at this pixel location an indication is present, then obviously there would be a sound path from this source to this pixel location to the receiving element. If nothing is there, then I would receive nothing. But if there is something, then I know that at a certain time, which I can calculate, I would receive something that corresponds to this pixel. So basically, to make it a bit simpler, I have this illustration, and here you can see what I mean. If I fire this element as a source, and I create an ultrasonic wave, that ultrasonic wave is basically spherical because this element is very small. Then the ultrasonic wave travels through the material to this pixel location. And again, if there is an indication at this pixel location, you would get a reflection that travels back to the array. And you can see that if I listen with all these elements, then I start to receive responses. Now this element, for example, because it's closest by, it will have the soonest response, the earliest response, and also the strongest response because it's closest by. Now you can understand that, for example, this element, if it's a receiver, then the travel time is simply longer, and I see later in time a response. And you get this particular patterns. Yeah. So for example, if I would have another pixel, maybe here, then this pattern would be a bit different. So basically, this type of pattern, I always like to refer to it as an ultrasonic fingerprint. But in essence, this ultrasonic fingerprint is nothing more than ultrasonic responses at a certain time. Now again, I know, because I know my model, that if this pixel has indeed an indication, then I know at what time this response would be. Now that gives me the following opportunity. If I know the travel time, that means that I can compensate for it. And this is also where the term IWEX comes from. It stands for inverse wavefield extrapolation. And basically what it means that I have this pattern, which is nothing more than travel times. I can calculate which travel time it would be for this pixel. And then what I can do is I can basically inverse the clock and shift all amplitudes back to time 0. And that is what I can do for this pixel. So if I do that, and indeed there was something here, then that means that all my responses would line up nicely at time 0. And then what I do is I just sum all these responses together, and then that response is assigned as a value to this pixel location. Now, obviously, in this illustration, I have this element as a source and all the others as a receiver. And I can do the same process for this element as a source and all the others. So basically what I can do is I can make combinations of sources and receivers. And if I have, for example, 64 elements, then I can take 64 square times the combinations. And all those combinations is called a full matrix capture. Yeah. Now, you might have heard about the term full matrix captures earlier, because I like to believe that the full matrix capture approach is one of the latest developments in ultrasonic technology. Also IWEX is basically introduced by A+RTD. But the philosophy of imaging based on full matrix capture data, that is something that is not solely unique by A+RTD. And we see that it's also being adopted by other companies. And that, I believe, gives credibility to the technology. So one of the things that becomes just a bit more complicated is that obviously waves, they travel not only directly from this indication, from this element to the indication, but we also have a back wall that acts as a mirror. So basically what you can say is that if you have a travel path from this element straight, there are multiple travel paths possible. So we have the direct arrival, for example, but there's also a direct skip arrival, or a tandem, or a skip arrival. And basically that means that this pixel location does not have one line in our fingerprint, but it has multiple lines in our fingerprints. And by choosing our delay times, by choosing our inverse times, we can select which one we would like to have. And the reason why we would like to have that is because it gives us more information. It gives us information of the top of the indication, but it also gives us information of the back of the indication or the side. So the use of multiple modes allows us to look at an indication from different sides. And because of that, it is possible to image an indication without knowing the shape up front. And that is, for example, what I would like to illustrate here. So for carbon steel, for example, for the inspection, we have 10 different modes. This type of indication, for example, can be visualized with this type of mode. Yeah, so we have waves that travel straight to the back wall, then they skip at the indication, they skip back again, and then they move to the other side. That type of mode will give a very good contribution to our image of this type of indication. Likewise, this type of indication, for example, we have our direct travel path, which is this one, and that sees it straight in our direct mode. Then this one, for example, we can create it with a tandem mode, and because of the fact that we have all these different modes, we can actually combine them all together into one image, and that one image has the properties of the indication with the size, with the position, but also with the orientation. So basically, that gives us the entire image. And in contrast with the traditional ultrasonic method, that has many benefits. So that was a lot of theory. I realized that, but just to summarize the conceptual differences between IWEX and traditional ultrasonic technologies. So IWEX is based on an image reconstruction algorithm. So basically what we do is we have this ultrasonic fingerprint, and by the approach of inverse wavefield extrapolation, we are able to reconstruct the image, to reconstruct the data into an image. So the ultrasonic data consists out of combinations of transmit and receiver. So it's a full matrix capture data set. And that full matrix capture data set, that is really different from existing technologies. For example, the Polseco method, where we just have a laser-like kind of beam, or a phased array sectorial scan, where we have the same as the Polseco, but then it is, let's say, swiveled into a pie-shaped pattern. The full matrix capture, the fingerprint is basically obtained by using an array. And then we apply the elements as separate sources and receivers. And that is, again, one of the conceptual differences. The outcome and the big benefit is that we have representative images in 2 and 3D, and we can also display those in real time. So that is so much about the theory. Then I would like to share some examples with you from actual practical situations. We started with the development with carbon steel. The reason for that is carbon steel is ultrasonic friendly, so to speak. So we have good signal to noise ratio. Again, I explained that we need the model. For carbon steel cases, it's very straightforward to predefine our model and to do the measurements. Then we have a small, medium, and heavy wall thickness, because the reconstruction does require some preconditions when it comes to, for example, resolution. And intuitively, I think that can be understood. If you have a very heavy wall thickness, then you do not require the same resolution as, for example, a very small wall thickness. Very small wall thickness requires a higher resolution than a thicker. So that means that your inspection setup, the choice of your ultrasonic arrays, the choice of your frequencies, that depends on the wall thickness regime that you are trying to inspect. Now I start with the medium wall thickness range, and the reason why I start with the medium is that's because it is the most common for our practices. So what is medium? It's typically between 12 and 35 millimeters of wall thickness, carbon steel. Those are not hard numbers, so there's always a bit of a transition area. But commonly we do the inspection with a 4 megahertz probe. And here you have just some examples of
making time for us in your holiday. Please enjoy.
So here you can have you see some examples of actual indications in welds. The concavity, as you can see, is a machined, is an artificial defect, so it's not a natural defect. The defect that you can see here as a lack of fusion indication is more representative. And if you compare this indication with the actual scan, then you can see very nicely the back wall and the front wall. You can see the indication. And what I like about this illustration is that you can see the location, so that means the depth position of the indication. You can see the orientation of that indication, and you can also obtain the size from this indication. Now also you can see, for example, the geometry. Yeah, so this particular example has a small high-low mismatch, which you also can see in this image. Now here's 2 more examples. So the previous example was an example of a lack of fusion and a root concavity indication of a narrow gap, a J-prep weld. Here there are some examples of the V configuration, and here again you can see very nicely the cap geometry. It also reflects the shape. So basically the root reinforcement, the different passes of the weld, but also again, you can see that there's a nice lack of fusion indication, which has the orientation following the weld bevel, vary as 1-to-1. And again, I think it's fair to say that the interpretation of these pictures, let's say, it requires than traditional ultrasonic methods, because you can just see the weld and you can see the indication, the depth, the orientation, the height, everything is just almost 1-to-1 comparable with the macro section, with the cross section of the weld. So then this is an indication about the cluster porosity. The cluster porosity is typically in the volume. Now it's interesting to see that the image amplitude is a bit lower, and that is because the pores in a cluster porosity, they scatter a lot. So that means that the ultrasonic energy goes in all directions. And if it goes in all directions, well, that means that we might miss some of the information that we would like to have to get a good contrast, because it does not come back to our receivers. Is that a problem? Well, no, not necessarily, because still we can see that it has a very representative shape. We see the location in the middle. So again, I think these two examples illustrate nicely how you can see the difference between a cluster porosity and how you can see the difference between a lack of fusion indication. And that is basically what we would like to achieve. So I would like to move forward to a heavy wall thickness. I think the thickest we did in practice was about 60 millimeters, so quite heavy. And basically, if you work with a heavy wall thickness, it means that you'll have to scale up your setup. So that means that you'll need different type of probes. It means that you need different type of wedges. But nonetheless, the principles, they remain the same. Here you can see the scanner. So typically the scanners that we're using, they can accommodate small wall thicknesses, and small being, well, let's say 5 millimeter, all the way up to 60 millimeters. And you can see here again the guiding band. And here, it's very nicely to see that this indication in the root, again, it's imaged correctly. And also the size is basically 1-to-1 comparable to the actual macro sectioning. Having said that, it does require to use the right setup. So for example, if you would like to do an imaging inspection of this type of weld with a probe that is too small, then it would not be possible to get this type of information. So it is possible, it is important to use the right procedure and to use the right setup sequence in order to do this. Yeah. So although imaging has a lot of benefits that I am happy to illustrate here, it does require the correct knowledge in order to apply it. So then I would like to move forward to the smaller type of wall thickness, still carbon steel. Again, to be more specific, smaller means a wall thickness of 12 millimeters and smaller. I think the smallest that we did is around 5 millimeters for a particular kind of pipes. And for that type of setup, we're using higher frequencies. Higher frequency means a shorter wavelength, and a shorter wavelength means that we can be more accurate. Now, obviously, you can ask yourself the question, why wouldn't you use 10 megahertz also for the thicker stuff? And that in principle, that can be done, but it has some practical limitations. Practical limitations means that if you have a very high resolution, that means that you require a lot of pixels. If you have a lot of pixels, that means that the calculation becomes more time consuming. So the calculation is just more intensive. And that can have a practical limitation, namely that your calculation goes slower. So it really depends on the type of scenario, the type of inspection scenario that you would like to address. We have done inspection in offshore situations, for example, Offshore situations means time is money. So the inspection time needs to be fast. In that type of scenario, you would like to tune your setup in such a way that you can still accommodate the cycle time of the girth welding or of the welding process, so that you do not hold up the entire manufacturing chain due to the inspection. Well, there are obviously other scenarios that you can think of. If it's really required to have a very high level of accuracy, but you have all the time in the world, maybe you know, let's say 50 minutes for the inspection, or maybe half an hour. Well, then obviously you can decide to improve your setup by a higher frequency. So to share some examples again with you on the smaller wall thickness, and really you can see that the results are still maintained. So now we have an 8 millimeter small wall thickness, but the imaging of the indication is quite accurate. And I must say that for these smaller wall thicknesses, we have been able to size indications up to like 0.5 millimeter. That can be done very accurately. So it's quite impressive what the technology can do. Obviously, provided that you're using the right system setup, and yeah, the right frequencies and probes. So also, having said that, some words about sizing. The software that we're using is able to. What you can do with the software is you can just simply draw a box around the indication, and then the software basically snaps to the edges of this indication, and then it'll give you the height size. So that means that the interpretation is also software facilitated, which in contrast to traditional ultrasonics makes it easier to do the interpretation. What I was talking about here, you can see this is, for example, an indication of 0.9 millimeters, and you can see that it's clearly imaged. And again, the indication is still maintained. So even for small indications, it's very accurate. And likewise, the root concavity is very representative. You can see the shapes, all the features are there. So up to now, what I've shared with you are examples of practice, but they are in 2 dimensions. I have to look at my clock because don't know how much time I have. Natalie, do you know how much time I have for the remaining of the presentation?
Yes, you'll have 4 minutes.
4 minutes. Okay.
Yeah.
Well, actually, I was moving towards the conclusion of the presentation. So far, I've discussed about 2 dimensions, but what I would like to share with you is that if you have 2-dimensional images, then because of the fact that we have a scanner, we can actually merge these 2-dimensional images in 3D. And therefore, I would like to share with you 2 examples, 2 movie clips. This one was taken in Canada on a landline. So I believe it was a 42-inch, and here you can see how we, the guiding band of the scanner has already been prepared by the operator. Then the scanner with the ultrasonics, ultrasonic electronics, is mounted on top of the scanner, and here you can see how the scanner moves as a it's an orbital scanner, so it requires 1 circumference. Here you can see the 2-dimensional images, and then in real time we can switch from 2D to 3D, where you can have an actual 3D representation of the weld inspection in real time. So where you can see the indication in the weld. So basically, the upper part is the cap, and the lower part is the root. If there's a lack of fusion indication, for example, then we would see that in between. And in real time, you can rotate it so to analyze it. And also, it is recorded. So at the end of the inspection, we have a record which you can analyze later on, and you can make a report. So this video that I would like to share with you is on a spool base. So the previous was on a landline. The video that you see here is more representative for an offshore scenario, whereby the operator sits in a cabin, and there are videos to the firing line. And here you can see again, it's all real time. It's a very nice example of a lack of fusion indication, whereby you can see that the actual indication follows the weld bevel configuration. The final example, this is also offshore. This is a bit of a different setup. This is a linear scanner, and this inspection was for the seam weld. So basically this pipe configuration was pipe in pipe, whereby there were two scales consisting out of two girth welds and two seam welds, and also the seam welds needed to be inspected. So apart from the girth welds, it's also possible with this technology to do seam welds as well, but obviously it does require a bit of a different scanner. So I got two more sheets, and basically those sheets are about the industry acceptance. Because everything is nice. We have a new technology, but it will only be important to use it once it's been accepted in the industry. So the full matrix technology, IWEX being a member of that full matrix family, is becoming more and more accepted. There are, as we speak, codes and standards being released recently, and this is all very recently. So we're talking about, what was it, 2020, 2021. So in the ESME code, there are some sections added covering full matrix capture, but also in the ISO. And I think that you know, allows the use of the technology in the industry because of the fact that there are codes and standards. Then when it comes to qualifications, the system that we're using has also been qualified by DNV, and those qualification standards are pretty common in the offshore. For example, carbon steel or CRA, that requires a thorough qualification program, and well, the IWEX technology has been subjected to those programs, whereby the reports are available. So thereby I would like to conclude my presentation. I hope it was informative to you. There's already some words about the summary, but at this point in time, I think it's nice to, you know, open up the discussion, and therefore I would like to give the word back to the chair. And obviously I would like to thank everybody for their attention.
Okay, thank you, Niels. Thank you for this very incisive and very good presentation. It's very simple and very clear to me, especially, and I believe it's also very, very clear to everyone. Quickly, I will just in 2-3 minutes give a quick summary of what you have said in the last couple of minutes. If I go by my own definition, I would say that what you are trying to describe, what you have just told us this afternoon, is the testing and analysis for welding defect and discontinuities in pipeline without causing serious damage to the original part. That's the quick definition I will give it to. Your presentation is divided into what I call about five sections: the basic concept, the principles of ultrasonic imaging. You gave some field examples, how is it accepted in the industry, and of course you highlighted some of the benefits and you summarized. Under the basic concept, you enumerated on the need for a proper QA, QC or pipeline welds in order to avoid failures which can pose serious threats to our health and safety, and of course, ultimately economic and environmental damage to our environment. You gave some quick examples of the pulse echo as well as the TOFD. Looking at the principles of ultrasonic imaging, you talked about how it works, and you made a comparison of the IWEX as well as the traditional ultrasonic testing. You gave some very good examples of the field example of the carbon steel welds for small, medium, and heavy wall thicknesses, which is really, really very, very interesting. I mean, and of course, you talked quickly about the acceptability in the industry and all the various standards, the ISO standard, the RTD qualifications that this current technology presently enjoys. And you looked at the benefit as one of the benefits I saw you talking about is the ability to be able to match a 2D imaging into a 3D image in real time. If what I've just said is correct, I will leave the floor to the public secretary. We take us through some of the questions that the audience may like to ask you. But before I close, before I allow him, my only question is: are you in partnership with IWEX Geo Solution? Because I saw IWEX Geo Solution on the flyer. I mean, I just wanted to find out.
That's a good question. Maybe one of my colleagues is able to address this question.
Exactly.
Yes. Yes. Mr. Jibola, yes, we are in partnership with A+ Veloci.
Okay. No, well, thank you so much. I'm not surprised with my friend, my brother, Peter Macaulay. I just wanted to find out and to especially thank you for what you are doing for our industry, because this is really bringing value to the industry. And what you have done over the years, even trying to showcase some of this technology at NAPE event is highly commendable. And I want to tell Niels and your colleague and the company where you work, you are with the right partner, without necessarily selling Peter Macaulay's company, but I've done a lot of collaboration with him, and he's very reliable. And I believe bringing this technology to the industry, especially in Nigeria, I don't know whether it is presently being used in Nigeria. It would be a good thing, probably at one of our conferences, to come showcase even to a bigger audience. That's just my quick remarks on your partnership with IWEX Geo Solution. Thank you so much, Mr. Peter Macaulay. Public Secretary, please, you have the floor. Go ahead, please.
Thank you very much, my chairman. Okay, so we have a number of questions. Okay, yeah, 2 questions on the chat. So I'm just going to read them out. The first one, the 3D image is breathtaking, but what was the thickness and scan speed for that particular scan shown in the presentation?
Well, obviously, thank you for the compliment. I'm not sure which example you mean. Maybe the one from this. But typically the wall thickness that we're dealing with is let's say from 5 to typically to 35. That is let's say the typical range of wall thicknesses. Then the inspection speed. The inspection of one weld ranges from 1 minute to a couple of minutes, and that depends obviously also on the diameter. If you have a very large, maybe a 42-inch, well then obviously the weld is much longer, so it just takes longer to do the entire circumference. However, the equipment was designed in such a way that it is faster than the welding. So obviously we understand the business requirements, which means that the inspection should not be on the critical path. So with all the examples that I've shown, the IWEX inspection is fast enough to meet the client's requirements in terms of cycle time. Is that sufficient answered for the audience?
Hi, Gokul, do you want to just quickly mute and just give me a confirmation? Oh, yes. Okay. Thank you very much. So the second one, can the FMC IWEX methodology be used on anisotropic carbon steel materials? So that's thermomechanically controlled process steels, like here, and have reliable examination results?
The answer to this question is yes. So the methodology indeed works with on isotropic carbon steels. However, it does require adaptations in the model. So we know that anisotropic model, anisotropy basically means that the sound velocity in a material is not constant. Yeah, for some materials, for example, that are manufactured by means of rolling, then you get, let's say, a rolled, a layered structure in the a layered structure in the metal, and that causes the ultrasonic waves to kind of bend. So this bending effect, this anisotropy, that is something that can be incorporated into the model. And as a matter of fact, in our ultrasonic software, we have already such functionality where you can set the level of anisotropy, and then the model indeed incorporates the anisotropy and calculates the delay times correctly. So yes, it is possible, and we, as a matter of fact, have done already some project with this. But it does indeed require some adaptations in the software, which we have. And I mean, feel free to contact us for some examples of that. Also, we are always happy to discuss and see what we can do to organize a demonstration of the equipment.
Okay, thank you very much. So there are a series of questions, I think, here by Mr. Chibuzo. I think maybe I'll just take some, maybe 3 at once, so that you can answer them. I'm just looking at the time, so by 15:05, we're looking at wrapping up the question section. So for the first one, what are the benefits of this tool over existing ultrasonic technologies? I think maybe I will just add to that in terms of like what's the cost benefit? So why spend extra for over existing ultrasonic technologies? Now the second one is, what is the sizing accuracy of the technology? Has the technology been used for sizing SCC colonies?
Okay. So let me see if I can address these questions in a time-efficient manner. So when it comes to the benefits of the tool, and obviously there are technological benefits, and I think my presentation was more emphasized on the technological benefits, but also it should have economic benefits. One of the main benefits that we see compared to traditional ultrasonic technologies is that for pipeline inspection, you always require calibration blocks. And those calibration blocks have targets that are depending on the weld bevel design. So they are costly. With the IWEX tool, because we are not depending on the weld bevel configuration, we don't need that type of calibration block. As a matter of fact, it would be possible to make a scan without a calibration block at all. So just on a bare pipe. That's the only thing we need to make a system setup. Now the economic impact can be very substantial, especially if you have a project with a lot of different scopes, which is sometimes that we see there are a lot of different lines in one project. There's the pipe in pipe, there's the main line, and then there's the feeder lines. Sometimes during a project, there can be many different configurations, and for all configurations, for a traditional inspection, you would require calibration blocks, and with the IWEX technology, that can be reduced significantly. So apart from the technical benefits, of the ease of interpretation, the economic benefits and the operational benefits can be quite substantial. That is also the reason why we see a change over from the traditional technology towards this type of technology, because it can be, as a matter of fact, cheaper than existing technologies, depending on the scope of work, obviously. So when it comes to sizing, the sizing accuracy, in general, you can say that the sizing accuracy is better, but it's not that it's let's say a factor 10 or so more accurate. I must say that if you have a good work practice based on a traditional method, so for example, the zonal discrimination method, if that method has been calibrated correctly, if the setup is okay, if you would follow the best practice, then you can achieve a sizing accuracy which approaches the what is, let's say, physically reasonable, because there's always a physical limit of accuracy, and that depends again on the physics. But with IWEX, it's just easier to approach that limit than compared to traditional. So what is the sizing accuracy? In general, it's let's say 1.5 times better as a rule of thumb, but it's not that it's, let's say, a factor of 10 or of 10 better. That is not what I would like to claim. Has the technology been used for sizing SEC colonies? Answer is yes. We have been working together. We have been involved in projects organized by PRCI, so that is the Pipeline Research Council International in the United States, and they organize joint industry projects that aim to solve challenges in pipeline industries, SEC colonies being one of them. There are reports available, so I'm not sure if the one who asked this question has access to files of the PRCI. If not, feel free to contact me, and I would be happy to share some of those results on the performance of this type of technology on SEC colonies. Can bends be scanned with IWEX? In principle, the answer would be yes. But that will be something that we haven't done that often. So that will be something where I would like to recommend a feasibility study first. So the minimum OD that can be scanned, I'm not sure if there is a minimum OD. It's more related to a practical situation. Yeah. So the minimum OD that we have scanned is about 4 or 5 inch. And that is typically, depending on the kind of manipulator. So you would use chain scanners, smaller probes. Obviously, you would use wedges that are curved to accommodate radius. So it's not necessarily a principal limitation. It's more a practical engineering challenge that you need to address in order to do that. So again, I would like to invite the person who asked this question to contact me and try to understand what is, if he has a specific application in mind with a minimum OD. Okay, then can duplex super steel be done? Can this be applied to in-service assets only on CAPEX projects? Answer is yes. Super duplex is something that we've done before. I have to say with it is more challenging because super duplex, especially the welds, have the property that the grain structure is typically coarse. So that means that ultrasonic waves attenuate and they scatter. So there are good solutions to overcome those issues. And when it comes to super duplex or to duplex stainless steel, we have experience with that. So also when it comes to this type of applications, I would like to invite the person who asked this question to contact me so that I can show some examples of that. Unfortunately, as you already noticed, I like to talk about this, but I have to be respectful for the time. I decided to keep this presentation on carbon steel only, but there's also other application like the seam weld, like the SEC, like the duplex, and I have presentations of that as well. So maybe also recommendation to the chair. If there's any opportunity for a presentation, bear in mind that we have more of this type of presentations on other applications. So then the portable. So the equipment that we have demonstrated today is for the main application is for automated girth weld inspection. Indeed, we are working on a portable version that is battery powered. That is still work in progress. We have the first prototypes already, but I have to ask my colleagues when the planned date for release is. Something I don't know from the top of my head. But one thing is for sure, it is coming. So that's something I can say about it.
Thank you very much, Neil. We appreciate the presentation and also too for taking time to answer all the questions. Thank you very much. And thank you everyone for your time. So quickly we'll go to the next, we're about wrapping up. So we'll just do a quick announcement, have a speech from the president of the Nigerian Association of Petroleum Explorationists, Mrs. Patricia Ochibu, fellow NAPE. And also we want to, before we go into the announcement, we want to use this opportunity to acknowledge all the NAPE fellows that are on this call. NAPE chapter coordinators. We have chapter coordinators from Warri, from Warri, from Abuja, and other places join our meeting. And also to want to thank our publicity secretary, the NAPE publicity secretary, Mrs. Tubosu Afamaya, for attending also. And also we would appreciate our program chair, who is Mr. Ajibola Oyebamji, fellow NAPE. So with that said, I'll just quickly go through our, please, Neil, can you stop sharing so I can, okay, I think I can take over, yeah.
There you go.
Yeah, thank you. So, okay, so just go through the announcement. So just a quick one, I think it will be, because there are a lot of people who are on this call who might not have come across NAPE. So NAPE is the Nigerian Association of Petroleum Explorationists. It started as the Lagos Society of Geologists and Geophysicists by a young man named, of course, who is now elderly, Ako Meno Oteri. And the name was changed to accommodate colleagues in other parts of the country. So it was established in 1975. And at the moment, we have over 10,000 strong individual members and close to 200 supporting corporate members. Your company could take advantage of our association in terms of the varied members that we have in signing up for corporate membership. So our vision is to be the preferred professional petroleum geoscience association with a global reach. We have a lot of people from different parts of the world attending this meeting, people from America, Asia, and Africa, and I think also from Australia. So yeah, we have we have that global reach. Our mission is to promote the study and practice of petroleum geosciences for the benefits of members and other stakeholders. I think right now with the transition to cleaner energy. I think, yeah, even though we're petroleum focused, we are still an we're energy focused too. So you might be considering, how do I join NAPE? How do I become a member of NAPE? It's quite straightforward. It's just for you to fill in the membership application form. If you want to go through that, you can speak to myself. I'll be happy to leave my email address. You already have my email address because I've been communicating with you, trying to remind you to attend this meeting and through the registration. So you can always reply to that email, and I'll be happy to put you through the membership. I'll forward it to the appropriate quarters for you to be able to do that. If you're looking at also corporate membership, that's also available. Yeah, consider the fees. They're nothing compared to what we pay in other association. It's around it's less than £20 and less than £80 for corporate memberships. So I'm sure you've enjoyed this meeting. So we have other technical meetings by other chapters. So at the moment, with the benefit of online meeting and all the online platforms, you can join other technical presentations hosted by our sister chapters. So we have one organized by the Warri chapter, taking place on the 27th of July at 11 a.m. The title is Boosting Reserves Through Seismic Technology. So if you're interested in that topic, you could simply go into the Zoom link. You could take a screenshot for you to have access to the Zoom link. We also have a special technical session in honor of Dr. Emmanuel Eno, who is a fellow NAPE. He's celebrating his 70th birthday. So that's taking place on the 28th of July at 11 a.m. So the title of that talk or the presentation will be the academia, would be its story, its journey from academia to the oil and gas industry. You could also take a screenshot for you to have the Zoom link. You don't need to register, it's just for you to have the Zoom link and simply connect. We have also another technical meeting which will take place on the 6th of August. It's organized by the Uyo Calabar chapter. The topic is climate change impact, a geotechnical perspective on management strategy of critical infrastructures of oil and gas industry. The link to register can be found on our website, on the NAPE website. So if you want to attend, you could also contact me and I'll be happy to link you out to the appropriate portal. So for NAPE, we've also got relationship with other professional bodies like the American Association of Petroleum Geologists. We have our young professionals. They've organized a boot camp where you can learn Python computation. So for this, it's going to take place, it's going to commence on the 17th of July. So that's, I think, yeah, that's a few days from now. And the fee for that is we're looking at around less than 25 pounds. If you want to register for this, it's a 6 weeks course. And if you want to register for details and also payment, you could quickly screenshot this for you to have the link. One of the benefits of being a member of NAPE, especially when you're based in Nigeria, is that you have insurance. So please, for those who are interested in this, take note of this, the NAPE Health Maintenance Organization scheme. Each year, we organize the annual, the international conference and exhibition, which the chairman of this program mentioned briefly. So there we invite people to present. There's exhibition, there's sponsorship. Currently, there's we have the call for abstract. The deadline has been extended to the 25th of July. If you're interested in this conference, you want to present, kindly submit your paper quickly. Kindly submit your paper. And also, if you want to sponsor, kindly speak to us. That you can speak to me, and I'll also link you to the appropriate portal. So with that, thank you very much. Please watch out for the next NAPE UK Europe chapter. I'll be sending an invite once we have that organized. And this will either be communicated via email or WhatsApp. Thank you so much for attending this event. Now I will just hand us over to the NAPE president, Mrs. Pat Uchebu, for her to give a speech. Thank you. Hello, ma'am. You're still muted, ma'am.
Yeah. Good afternoon, everyone. I'm delighted to have been part of this meeting. Thank you to the speaker, and thank you to all the people who stayed throughout the presentation. It just goes to show that there's a lot of opportunity for every geoscientist who is willing to work. As usual, we are NAPE, and you've heard about everything we are doing. I think you should stay tuned to hear more about our upcoming conference, which will be in a hybrid form. We're going to be live in Lagos and also online. Thank you. I wish you all a very good day. Goodbye.
Thank you very much, Ma. We appreciate. Just before I invite the publicity and the General Secretary to give the vote of thanks, I just want to quickly answer some questions that are on the chat, and also to just make an announcement too. So in terms of the recording of the webinar, yes, I would send that to us. I will send it to your email, provided you registered. I'll send that to you. I just want to also mention that our next technical meeting for the UK Europe chapter is planned for the 25th of August. And also we're planning to have another one next month. In the month of September. So that will be communicated. So I'll just call on the General Secretary of the Association, Mr. Gideon Giwa, to give us the vote of thanks. And after that, we will have the networking session where we can interact. Thank you.
Thank you, Opeyemi, and good afternoon, everyone. On behalf of the NAPE UK chapter, I would like to express our gratitude for joining us today. We want to thank our speaker, Dr. Portzgen, I hope I got it right, for a very good presentation and the discussion as well. It's always a pleasure to have you. And as Opeyemi has announced, we look forward to having you again next month and in September as well. All will be communicated through the appropriate channels. So on behalf of the Executive Committee of the UK Europe chapter, I wish to express our sincere gratitude and wish you a lovely afternoon, and see you next time. Bye. The session is now open for networking.
Thank you. Thank you.
Good afternoon, Gideon.